Hello and welcome to Dendrite Digital in Santa Ana, California. This is a deep dive into the 6502 processor in JavaScript with WozMon. WozMon, of course, is the uh, code that Steve Wozniak had written for the Apple I. Today, the disassembled code here for WozMon starts off with a CLD, clear decimal flag, CLI, which is to clear out the interrupt bit on the status register of the 6502. But let's just see what this code does for a little bit. If we type, say, FE00 dot FEF7, we get this. And this D8 right here is this D8 right here. And this 5-8 right here is this 5-8 right here. CLI. Now I moved WozMon up to FE00. But yeah. So what else can we do with this? Well, we can examine, let's try 40. I have a sample code that I had rewritten, just a short little program. Got an A9, yeah, just these looks like 15 bytes of code, and let's say let's just run it. So this is what this subroutine is doing. It goes and puts up all the characters available to WozMon. It's not finished yet. There's a gap. I put it at the return so it have a cleaner display. But yeah, let's just wait till it finishes. Now, the whole time it was doing this, the reason it was so slow is because it was disassembling it as it ran, and also displaying the 6 registers of the 6502. So you can see up here, yeah, here's the entry point at 40. And it loaded with an 8D, which is a printable return character. So it jumped down to the next line with this echo. So add 0, which basically says when the carry is set, this is add with carry. When the carry is set, it adds 1 to the number it's adding. It's carry input bit. And then we compare it to AD, which is the same character here, but it's added 1 to it, so it's going past this. And you can see here that here we have AD in the accumulator, and after the add, we have an 8E. Well, that's not equal to D, so it loops back around. The sample program I saw online that this originally came from had a bug in it, so you couldn't finish it, couldn't get it to work unless you spotted that it was looping back to the point where it loaded A with a 0 and went through all 256 characters. The reason I started with 8D is I wanted it to return after the command I entered. And so it would return, and then it would print out the characters up to the return character again, and then it would loop back around from FF to 0, and then it would go all the way up to code 8D, and then this loop would fail. Yeah. So here you can see that the accumulator equals 8D, and the loop doesn't happen because it's equal to that 8D. See right here, A equals 8D, and compare it to 8D. It is equal, so it drops through to the next command, and that's jump back into WozMon at a safe address. Interesting little program. It was originally different. It didn't work the way I spotted it online, so I had to fix it. And so how do I make this magic work? A 6502 in Chrome browser, this HTML file, and yeah, it's just this processor. Now it says 65816. It's not quite there yet. How does this work? If we go into BB Edit and we click on JavaScript, the JavaScript version of the CPU, these are the flags, and E is normally presented in a different way. And I have the values 0 and 1 as literals, and I'm bumped all the bits in the 6502 up by 2 bits. And so N is outside of a byte. It's outside of the low byte. But my registers are like 32 bits. I haven't modified the 6502 to work with 32 bits, but 32 bits in every register. And I might even go 64 and modify how the 6502 the addressing modes and the mathematical operations, I might bump up to 64 bits too. Yeah, I might have my own version of the 6502 as the 65 B64. But I want it to be at least code compatible in the beginning. Here's all the global variables I'm using. Labeled them, call them up in any of the subroutines, or even the graphics processor. I could probably find a way to use these as they are and just import them somehow as global variables. I'm not too into object-oriented programming. I know how portable it is, and I just haven't learned to code that way. This probably opens the door for all kinds of chicanery, but I'm just writing this code for myself to share online in a safe manner. Here's the main routine that the main tick of the clock sort of routine. Yeah, and here's the trace on element here, and here's the this turns trace on and run off, and that way it just lists the code until it runs into a break, and then it goes back to the beginning. It goes to the reset vector and goes back into the WozMon code. First thing first, in the clock cycle, after the initialization procedure, we have load the opcode from the program counter address. And then here dat is the actual bytes in the program. Here it's doing the address. Here it's putting the hex code of the operation. We're checking if the program address has a label. If not, it puts in 12 spaces. If it does, it's going to add spaces until it equals 12 characters wide with the label in there. Yeah, and then increment the program counter Make sure it's within 16 bits, and then cycles. This is part of the way that we keep the timing correct. Is we add to the cycles on every pass, and I might even have to synchronize the graphics operations so that the cycles are true. Yeah, a lot of games use that. Um, a lot of games use that race the beam sort of programming. I haven't done much of that. You know, I started on the Atari that used those almost exclusively. I just learned to program it a different way, and I made maze games and all original code. I didn't bother like trying to disassemble somebody's cartridge and make it happen for me personally. I'm kind of against that. And WozMon is public domain, so sure, I'll use public domain stuff, but I don't want to step on anybody's copyright toes just so I can brag about how I cracked this game. I've seen a number of videos online about on YouTube and elsewhere about how these games work, and I can appreciate the ingenuity in that race the beam sort of process. I just didn't want to count every cycle and figure out, where's the scan line and what pixel out is it, and just time it so it happens, so the code does its thing right at the point that the screen is being drawn. So yeah, there's the clock, and here's the trace operation. I might call it Tron instead of on with two N's. And here's the create routine. All it's doing is loading that sample code at 40 right here. Load the WozMon code. Reset. I have a palette. I have a 256 color palette. It might I might have this palette correspond to the Atari 2600 palette. It only had 128 colors. I think it was 16 colors and 8 intensities of each color. So I might bump that up to 16 intensities of every color. And yeah, I might do that. And then here it is putting the program counter in the address. Yeah, this happens right after the initialization procedure. Got sample code, Wozniak, WozMon, reset, palette, ADR, and then it's ready to go. Let's look at fetch. So fetch, lining up the address to have the number in it. And if it's accumulator addressing, then put the accumulator in fetched after it's already read it. So just write over it with the accumulator. Yeah, here it is. Fetch a number of bytes. So that number, if it's 2, it fetches another byte from it. And it's not an accumulator addressing. So later we're going to look in some future episode. I'm going to upgrade this to the 65.816. So I'm already trying to do that. So here's get flag. It just pulls a bit out of the status register and puts the value into the return value. And if it's 1, it returns a 1. If it's 0, it returns a 0. And the 0 happens here, even if it's false. So yeah, if this is 0, it's not true, and so it'll put out a false. So the again the flag 0 and flag 1 are literal, and otherwise it fetches the value of the flag at a specific bit position, and then set flag. We're taking the value of the flag and we're ORing it. We're ORing it with the status register, and here we're turning it off. We're inverting the value of the flag. We're taking all the positive bits and flipping them to 0, and all the negative 0 bits and flipping them to 1. And then we're ANDing it, so it's clearing the values in that's here. And the label. This searches my my table of labels. It's expandable. You can make it as many as you like, and it does a binary search through it. So it takes the length of my array, and it shifts it down by 1, and then it sticks it in I, and that's how I get these labels to pop up. And then here's the differential. Yeah, we're taking the length of the labels, dividing them by 2, and then finding the middle, and then setting D to half of that again. And as long as D is greater than 2, it's going to do this. And so it finds, it does a binary search through all the labels, so it's really fast. 65,536 labels, one for every address. You'd have 65,536. It would only take this 16 passes to determine what the label is. Even with just, suppose you had like an impossible number of labels, like 2 to the 64th power labels. Again, this would only take 64 passes before it knew what it is. Instead of going one by one, is this the label? Yeah, worse than bubble sort. Jesus. And then yeah, here it's just fine. It's just doing a binary search, and when it's over, it adjusts, where it is in the list, and then it outputs the label or -1 if we haven't found it. So, and then here's load segment. You saw that in the create routine. It's just going through a text file, and the text file is a certain format. Let me show you that format. Yeah, see, here's the WozMon code in a string format. The whole thing with JavaScript and a lot of other languages is they add a whole bunch of characters to things. The 0x for the hexadecimal, and I know why they're doing that, but still, it's like, and you can convert them back and forth to string and just the byte. Yeah, so 2 4-bit numbers in for a hex code. And then we have a 16-bit address, 4 times 4, 16. So 16 bits for a 2-byte address. I might make that 3. I might make that 3, like a 64, 65 816 or 65 802. But yeah, yeah, and here's the opcode list. So you have your opcode and then your implementation. This is implied direct index X, indirect direct index. I don't know. They in the documentation, like over here. While we're thinking about this, let me show you what I have to do. Here's actually what we're running. It's not the 65 version. It's this CPU version. And if you look here for 9C, yeah, 9B is actually what we should be looking for. Yeah, so trade to X to Y is over here with the 6802 and the 68816 or 65816 and 9B. Let's look. 9B. Yeah, here it is. So here it says trade X to Y, and we'll just do that here. We'll just trade X to Y. Now I don't have that function here. I don't have that function here. So let me come up here just to trade X to Y. We have to go trade. Let's go to keep it alphabetical. So let's copy this trade Y to A. Copy, paste, paste. Trade X to Y. Trade X to Y. Trade X to Y. And we just change what it does. We want this into Y. This comes from, oh, let's make it lowercase. Gotta be case sensitive here. Trade X to Y, and then we reevaluate the Z and the sign bit, the 0 bit and the sign bit, and then we return. And that's all conditional if you're running it. Run is a flag that tells you whether the code is active or not, whether the trace is on or not, and I might have to adjust these to be sensitive to the various flags in the 65816. It's not there yet. Still working on it. So what if we kind of try to hedge the bet and see if there's a trade Y to X? Let's trade X to Y. Trade Y to A. Trade Y to X. Yes, there is. So it's at BB. Let's go find that. Trade Y to X. Trade Y. Let's come down here and do another paste. Trade Y to X. Trade Y. X. And we go down here. Trade Y. X. Trade Y to X. It's just not what I did. Yeah. Okay. Sorry this is uncut, but I didn't script this. I'm just playing it by ear. Yeah, so these are dressing modes. I need to update those too. There's probably a few of them here left, um, like ILY. I don't know. Maybe. Apparently that exists because otherwise it would halt the code and issue an error message in the browser. See, JavaScript is the language to use. All the other, C, C Sharp, Swift, all of them are locked into a specific set of hardware for the Apple or Microsoft or somebody is the they're locking them in. A long time ago, when JavaScript was new, they were all panicking, thinking, "Oh, these guys are gonna take they're gonna take over the operating system stuff." Well, here it is, 2024, late 2024, and finally, I'm doing this. I want a as you type compiler. As you're typing the code in, it 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 goes and inserts the new stuff into the old code, and you just it's live. It's like BASIC, except that it's machine language. You type the machine code in, and you can even do this with the high level language. You can have a high level language that puts the code in as you're typing it, and it would be so much easier than having these gigantic text files all, dependent on each other, and the make file doesn't run because Apple is blocking it. Where's we need you try to compile the code on a Mac, and they lock it up with like we don't know where this code came from, so you can't run it because it's probably not Apple software, and we don't want anything but Apple software running on an Apple. But the web languages, yeah, the web languages have to work because otherwise, the internet wouldn't work with you. I don't know if Apple's going to try to take over the whole coding thing with JavaScript, because that would be very scary. Nothing but Apple stuff works on an Apple. How infantile.